In the process of building our team's ground control solution for the UAVSI SUAS drone competition, we ran into a number of design challenges. Our stack required multiple complex components to interact with the drone. For example, telemetry logging and path planning components, and other data connections for visualization and competition mission data. Considering these requirements, our team decided to experiment with using a data distribution system, or DDS, to integrate these services. The standard DDS framework for robotics is ROS, the Robot Operating System. ROS offered powerful multi-drone control and communication features, and a huge ecosystem of libraries in support. So why didn't we use it? We discounted ROS fairly early on because we found it to be too opinionated. A big pain point was ROS's tying of distributions to specific Ubuntu versions, which we found to be too limiting for our team to develop effectively on. Another problem was, ironically, that same batteries included principle. ROS essentially has its own tools for everything, and we viewed it as carrying far too much technical debt to integrate effectively into our stack.
At the same time, our team has been highly involved in the development of the new UAVCAN v1 communication protocol standard. For those who are unfamiliar with the project, UAVCAN, which stands for Uncomplicated Application Level Vehicular Computing and Networking, is a distributed communication protocol. It is designed to facilitate robust interoperability between software and hardware nodes in vehicular networks, originally designed for the controller area network bus. While the technology is not new, a completely new version of UAVCAN, named UAVCAN v1, was completed in 2020 and is currently in release candidate, replacing the legacy UAVCAN v0 framework. v1 implements multiple benefits, including a more flexible protocol, first-class support for third-party and vendor data types, and support for different transports, including the new CAN-FD and UDP-IP.
One of the strengths of UAVCAN is its high-level publish-subscribe abstractions, which allow the building of powerful distributed systems that can nevertheless run on very constrained systems. Like ROS, UAVCAN facilitates publish-subscribe communication on subjects or topics between nodes. Instead of topic string names, however, UAVCAN subjects are identified by numerical subject identifiers. Similarly, UAVCAN nodes can also send requests, identified by numerical service identifiers, to other nodes and receive a response. Combined with UAVCAN v1's new ability to work across multiple transports, including UDP-IP, we decided to experiment with building a DDS for our ground control stack based on UAVCAN.
To develop the DDS for our ground control stack, we use PyUAVCAN, the reference Python implementation of UAVCAN that allows us to create and interact with nodes very quickly. Specifically, we began development with a bridge node, an application that would serve as the entry point for data published by the drone into the Pilot backbone. The objective of the bridge node is to serve as a broker between the Mavlink communication link to the vehicle and Pilot's internal DDS. We started the development process by writing custom UAVCAN types corresponding to common Mavlink services. The next step was to write the actual implementation for the DDS using PyUAVCAN. Specifically, we developed code to create a node and connect to the drone over UDP, along with a number of asynchronous publisher functions. Each of these functions listens for updates published by the drone to a certain telemetry, mission control, or other service topic, creates a UAVCAN publisher with the corresponding UAVCAN type, and then publishes it onto the internal UDP network. Something to note here would be that topics are identified by configurable numerical subject identifiers, or port IDs. So how are these port IDs configured? Similar to how ROS nodes have parameters, UAVCAN nodes actually have a registry, structured similarly to a dictionary, where register keys can be defined with corresponding values. These registers are configured to let the node know what port IDs to publish and subscribe to.
UAVCAN v1 improves on v0 in multiple ways, some of which were critical in allowing us to develop such a system. UAVCAN v1 expands the wire protocol to support multiple transports, most notably the UAVCAN/UDP transport, which the DDS system is built upon. Additionally, the introduction of runtime configurable topic IDs is crucial for allowing flexible flow of arbitrary data through Pilot's DDS backbone. Perhaps the most significant benefit of UAVCAN is the robust interoperability it provides across a wide domain. The combination of publicly regulated data types and vendor-specific data types allows different applications to work seamlessly with each other while also adding unique features. In the context of Pilot, this means more predictable, concise message sets that work consistently across different Autopilot and ground station configurations. Additionally, UAVCAN is being adopted on more and more vehicular designs, especially as autonomous vehicles get more complex. Sharing data types between Pilot and UDRAW, the work-in-progress application layer standard for intervehicular use, can lead to a more natural mapping between vehicular systems and ground station data flow in the future.
So where's Pilot headed in the future? The GCS is still in its early stages of development, and not all of it has been hashed out yet. Going forward, we intend to experiment with the UAVCAN ecosystem and its tools to more accurately determine the viability of a UAVCAN DDS. One tool we did not test yet was Yakout Orchestrator, a UAVCAN node orchestrator that could fill a similar role to ROS's launch scripts. Orchestrator massively simplifies the process of configuring port IDs for nodes, as well as other parameters. Another feature we intend to experiment with is auto-configuration node IDs. This would allow much easier dynamic addition and removal of nodes on the network. Such an auto-configuration approach could, on UDP, be implemented via a DHCP server on a similar protocol.
Overall, UAVCAN v1 shows promise in some applications as an easily deployable and less constrained DDS. Its interoperability with multiple protocols and its flexibility made it an appealing choice to us as a data backbone to implement a new, ambitious data-driven GCS. However, there are some weaknesses to this approach as well. One weakness is the relative lack of tooling for UAVCAN v1. Because only PyUAVCAN fully supports UAVCAN UDP on UAVCAN v1, our entire backend had to be written in Python, which produced noticeable bottlenecks in the message data rate, degrading performance. Furthermore, configuration of topics and nodes in UAVCAN is relatively complex, requiring the correct registers to be set on each node. Yakout Orchestrator may help alleviate this problem, which is something we will be testing in the future. However, in general, our work on a UAVCAN-backed DDS for our ground control system has led us to conclude that UAVCAN can be used effectively as a light, easy to deploy, and well-integrated data distribution system for applications.